start with graphs. So graphs are essentially a set of vertices connected by edges. They're like trees, but there's no hierarchy to a graph, unlike in trees. So let's take an example here. This is an example of a traditional simple graph. You can also have this directed. You can also have directed graphs, and then these can be weighted or unweighted. Usually, it's the directed graphs that are weighted, but unweighted graphs can also be weighted. Represent representing graphs. We can represent graphs in well a lot of ways, but we're going to cover three and go into depth into just two. One of them is adjacency list, and then adjacency matrix, and then you have edge list. Now, uh, so an adjacency list, you have uh, vertices mapped to a list of vertices they are connected to, or a list of neighbors. Right. So let's draw an adjacency graph for adjacency list for this. So you have A to B, B, A, and C, C, B, D, and A. Yes. C, D, and F. B, S, C, E, and F, and G. And then G is just back to D. An adjacency matrix, on the other hand, is a V by V matrix where V is the number of vertices. So you would just have A to G. Yeah. So none of the vertices are connected to themselves. Now A is connected to B. B is also connected to A because it's undirected. A is not connected to anything else. B is connected to C and A. Is there anything else? No. C is connected to D, E, and B. B. Uh, D, E. D is connected to D is not connected to B. Or is it? Yeah, it's not connected. C, E, F, and G. C, E, F, G. E is not connected to A or B. It is connected to C and D. It is connected to F. It's not connected to G. F is not connected to A or B. Just T and D. So it's not connected to C. Uh, it's connected to D. E. Not connected. And G is just connected to D. So that's your adjacency matrix. For directed, you would only mark one in the direction that the edge is in. So, for example, if this were a directed graph where A to B existed, but B to A did not exist, so this would be 1 and this would be 0. And similarly for weight, instead of 1, you would just enter the weight of the given edge. An example of a weighted graph would be the edges have weights and the edges are directed. So 0, 1 has an edge, 1, 0 doesn't have an edge, and that edge has a weight 3. 1, 2 has edge, 2, 1 does not, and so on. Now, for edge list, you just have a list of all the edges represented by what vertices they connect. So you would just have a list of edges 1 to 2 with a weight 1. Let's say 3 to 2 with weight 2. 0 to 1 with weight 3. 0 to 3 with weight 7. 1 to 3 with weight 4. 4 to 3 with weight 3. 0 to 4 with weight 8. And 4 to, oh no, yeah, that's it. Okay. So that's edge list. For an unweighted graph, you would just leave out the weight. It's assumed to be 1. And for a undirected graph, you would just include both directions. So 1, 2, 2, 1, 3, 2, 2, 3, and so on. So that's weighted under unweighted, directed, and directed, and the 3 representations we covered. Next, we have operations on graphs. For this, yeah, we have the list of operations here. These are pretty self-explanatory. Add vertex adds the vertex to the graph. Uh, Add edge. This is for the weighted edge. For an unweighted edge, you would just drop the W. Remove vertex removes a vertex. Remove edge removes an edge. Neighbors of a given vertex just gets you the list of all the vertices directly connected to the given vertex. Adjacent checks for adjacency, that is whether an edge exists between U and V, that is whether they are directly connected. Get vertices gets you a list of vertices, edges a list of edges. BFS and DFS are traversals of the graph starting from a given vertex. Num vertices and num edges just the number of vertices and edges. Get weight just gets the weight of an edge between U and V, uh, or zero if it doesn't exist. Degree of V. Now, degree of a vertex is the number of edges it is connected to directly. Number of edges. In degree and out degree are directed graph specific. They are pretty self-explanatory. In degree is incoming edges. And similarly, outgoing edges are out degree. So that's the list of all the graph operations. Now, let's take a look at implementations of these operations for adjacency matrix and list. So we have a graph. We have a graph where V is a set of vertices, E is a set of edges. We are representing the graph with an object that has the number of vertices stored, and we are just looking if the graph is diagonal or not. We are going to cover these operations: adding, removing vertices and edges, search with breadth first and depth first, and queries based on adjacency and degree of a vertex. For an adjacency matrix, we obviously need a matrix, and matrix of ij is 1 if edge exists or 0, and if it's weighted, it's going to be the weight of the uh, it can either be 0 or infinity for no edge. That is up to us. The space complexity is O of n square because we have a V by V matrix, or O of V square rather. So add edge. Uh, we are just making sure that the given edge is present present in the, the given what do you call it? Given vertices between which you're giving the edge is present in the graph. Otherwise, we are returning -1. Uh, if the graph is not directed, we set the reverse edge. We are setting U to V. And if it's not a directed graph, we are also setting V for undirected. For removing the edge, again, we check if the vertex is this and remove the edge by setting it to 0. And we remove the reverse edge if direct graph. For checking adjacency of two vertices, again, because vertices are present and return the work for both directed and undirected. Undirected is going to be 1, directed is going to be the weight of the edge. For getting the neighbors from the graph matrix, you have to go through the graph matrix of the given vertex and then uh, take the corresponding uh, column, no row, and look at all of them. And wherever there exists an edge, you're going to add it to a list of neighbors, and then we are going to return it. BFS and DFS, we'll get back to it after we've seen what it is. Now, adjacency list. Adjacency list, uh, we have an additional assumption of array of size n, where each entry is a linked list or dynamic array of neighboring vertices. The space complexity here is O of the number of vertices plus the number of edges. Because we're not storing the absence of edges, we're only storing the presence of edges. So here, if you want to add an edge, what you do is you do the normal check. And for the adjacency list of a given vertex, you're going to insert uh, at the end of the list the other vertex. And if it's not directed, you do the reverse. Similarly, for removing, you have the normal check. And then you find the vertex to be removed, V from U. And if the edge is present, you delete it. And if it's undirected graph, you do the reverse search, U from V, and it's obviously going to be present, but you do the check anyway. And then if it's present, you just delete it. Here, checking adjacency is not as easy. In the previous matrix, you could just check the corresponding row and column. Here, since we only store the presence and not absence, we can't delegate the check. To the list and find the edge. And again, work for both directed and undirected. Uh, from U to V. If it's undirected, V is obviously reduced. And if it's directed and U to V exists, well, it exists. As V to A exists, the search will not return true because that's a different adjacency list. Uh, on the contrary, getting the neighbors is easy. You don't have to search through the like you had to do in the matrix. You can just return the adjacency list as is. That's all the non-searching / traversal operations. The time complexities for these operations. Space complexity we already saw. Adjacency matrix is V squared. Adjacency list is V plus E. Mm, uh, Adding an edge is time complexity of 1 for both of them. Removing the edge is O of 1 in an adjacency matrix because you can just directly access it. Whereas in an adjacency list, you have to search for it. So it's dependent on the degree. Adjacency checking is of one in adjacency matrix. Adjacency list again you have to search through, so it's not instant. Uh, get neighbors is of mod v an adjacency matrix, and this is supposed to be O of one. You just return the adjacency list as is. DFS we haven't seen it yet. Adjacency matrix is best for dense graphs, and adjacency list is best for sparse graphs because if there aren't a lot of edges between the vertices, adjacency list is better because you're not wasting a ton of space storing edges that are not there, right? Now back to BFS and DFS. Now, BFS and DFS are traversals. Uh, there you go. So BFS is breadth first search. It operates on the principle neighbors first. DFS operates on depth first. So DFS is depth first. So it goes through the depth of the graph, whereas breadth first search is breadth first. So it looks at the neighbors each individually and then goes to the neighbors of the neighbors. Whereas depth first picks a neighbor, goes to its neighbor, and so on all the way down and then back up. And then continue with the next neighbor and repeat. So let's do BFS starting from 1 here. Uh, both of these have in common are visited with to keep track of which vertexes have been seen. So this can be an array of booleans for one for each vertex, or it can be a hash set to store, add vertices as you go on, right? Now, we start with one. You add one to visited, and then you look. You have a queue for PFS. So in the queue, you add its neighbors. 2, 4, 3, and from the queue, you remove the friend and repeat the process. So we are removing 2 from the queue. So it becomes 4, 3. 2 is now listed. Uh, Now we add the neighbors of 2, which is 8, 7, and 5, and 3. 3 is already in the queue. So 8, 7, and 5. No. Now you can remove from the queue again. So we get 4 visited and shift and the neighbors of 1 and 6 and 6. And then we want 3 and 3 are 5, 6 and 2. They're all in the queue or listed already, so we have nothing to do. And we add 8. Neighbors are 2, 6 and 7, either listed or in the queue, so we do nothing. And then we take 7. Neighbors are 8, 2 and 9. 8 and 2 are listed, 9 is in the queue, we do nothing. And then 5, 7 we added to visited, and 5 added to visited. 2 and 6 and 3. 2 and 6 is in the queue, 2 and 3 are invested, do nothing. Remove 9, neighbors are already in it, and remove 6. That's depth first. Depth first is the exact same process, but we use a stack instead of a queue. So by using a queue, you're enqueuing the neighbors, and the first thing you enqueued is ahead of the next things you enqueue, because that's how a queue works, right? By using a stack, what happens is, due to the first in first down principle, you go down the depth first. So you have a stack, you're inserting, say, 2, 4, 3. Sorry, last in first out stack. So the first thing, 1 is listed now. Next, you take 3 because it's at the top of the stack, and you add the neighbors of 3. 2 is in the stack already, so you add 5. 1 is already there. Yeah. And now you take 5. Neighbors of 5, 2, 6, and 3. So you add 6 here, and then the next you take 6. So you're going further and further in terms of depth. 6 has neighbors 4, 5, and 8. So next you take 8. 8 has neighbor 2, 6, and 7. And next up 7. 7 has neighbors 9 and 2 and 8. So you add 9. 9 has neighbors 4 and 7. 4 is already in the stack, you do nothing. You pop 4 from the stack, add it to the stack. 4 has neighbors 9, 1, 6. All of them are already, and you pop 2, and you're done. All the vertices are listed. So the only difference between breadth first and depth first in terms of implementation is that we use a queue in BFS to get the neighbors first, and a stack in BFS to get to the depth first. Uh, Adjacency matrix BFS. Yeah, there you go. So in an adjacency matrix, how you do BFS is you have a start node. You check if the start node is in the graph. You create an visitor. It can be a hash set or an array of booleans. We have taken an array of booleans. Uh, Create a queue to use for the BFS, uh, and we set the have to be true. And you need and queuing um, the start vertex to the queue, and we are saying has been listed. And until the queue is empty, we are going to keep dequeuing, and we are going to mark uh, u as visited. So visited of u is equal to true. Then I is equal to 0. And then we are going to iterate through all the um, what do you call it? All the vertices. And if there exists an edge, that is, we are going to find all the neighbors of u. If there exists an edge between u and I for all the I in the vertex set, and I has not been visited yet, we are going to nqi. And then we are going to say I has been visited. So this will prevent us from enqueuing the same vertex multiple times. If you say this is visited, the next time the second part of this condition will safeguard it from being added to the queue twice, right? And then we are just going to repeat it. So we take the first neighbor, mark it as visited, add its neighbors to the queue, mark them as visited, and repeat. So at the end, we are just going to return 0. So that's a breadth first traversal. This can be adapted to search for a node by just taking another node to search for. So we can just take an parameter v to search for. And then in that case, what you do you enter here, you just return true or false. So BFS can be implemented two ways. The first way would be just traditionally code as BFS except stack instead of a queue. Everything else is the exact same. So you're just going to add it to the stack and pop from the stack, and then look at its neighbor, add to the stack, and so on. Right. The second way is used to use recursion and use the call stack as your stack essentially. So in there, what you would do is you do the standard check, and then you create a visitor array, and then you call a recursive function that takes in the graph, vertex u, and the visitor array. What this recursive function does is it takes the marks u as visited, and then from I is equal to 0 to n, it's just going to check all the edges, and if an edge all the possible edges, and if an edge exists, it's going to recurse. And this recursion here is what provides us with the stack-like behavior. So this is our hidden stack through which we're essentially going down the graph and coming back up again. And for an adjacency list, the implementation is similar, but instead of going through the adjacency matrix and finding the edges, you can just go through the adjacency list and grab the edges. and the rest of the code is the exact same. When the queue is not empty, you're just going to dequeue, visit mark it as visited, and then go through the edges of the current vertex. And if it's not visited, you're going to enqueue it and mark it as visited. And DFS, same deal, both for recursive and the normal one. The normal one first. While the stack is not empty, you're going to pop it and you're going to mark it as visited, and you're going to go through the adjacency list and push them if it's not visited. Now, in the recursive, same deal. You create the visited array in a non-recursive function and pass it to a recursive function. The recursive function marks it as visited, and while this thing is just going to loop through the adjacency list, and it's going to recurse if it's not already visited. So BFS and DFS square because you have to search for the edges at each iteration. Here, it's going to take off v plus e time because in the adjacency list, you're just storing the edges directly. So just going to go through each edge individually. So that's BFS and DFS done. Yeah. Here we have a more comprehensive list. So adding a vertex in an adjacent list is for fun. In an adjacent matrix, it's going to be of v square because you have to expand the matrix. In an edge list, it's for fun because you're just adding it to the vertex. It remains unchanged. Removing the vertex of v plus e because you are going to have to uh, at worst go through all the vertexes if it's connected to all of them, and then go through the edge list and delete them. In adjacency matrix, you have to shrink the matrix, so deletion takes of v square. Or in the edge list, you're just going to have to iterate through the edge list and delete all edges that contain the given vertex. Adding edges of one in all of them because uh, to add an edge in an adjacency list, you just append. In an adjacency matrix, you just set the corresponding row and column. And in an edge list, you just append again. Removing edges of an adjacency list and edge list because you have to go through the list and remove. In an adjacency matrix, you can just unset the given row and column. So it's of one. Adjacency check is of v in adjacency list. Uh, that's the due to the worst case being connected, a vertex that is connected to all other vertices, and you have to go through the entire adjacency list. Adjacency matrix is just of one because you can just directly check the row and column. Edge list, you have to go through the entire edge list, worst case. Neighbors is dependent on the degree for adjacency list because that's how long the list will be. For adjacency matrix, it's going to be of V because you have to go through the entire corresponding row or column to find the whether the any wait oh sorry of one I got the wrong column. It's of one. You can just uh, oh you have to get the oh yeah you have to build a list. You have to go through and build the list. That's why it's of V. And O of E, you have to iterate through the edge list and get the neighbors of a given vertex. Getting the weight is O of V in an adjacency list to search through. O of 1 in adjacency matrix, you can just get it directly. In an edge list, again, you have to search through the edge list. Getting the edges from an adjacency list, you have to iterate through all the vertices and edges. So it's O of V plus V. It's O of V squared in an adjacency matrix. Edge list stores them already, so it's O of 1. Get vertices, it's just O of V here. It's O of V here. It's O of E here, assuming you don't store the edge. If you store the vertex set, it's going to be O of V. BFS and DFS. It's O of V plus E in an adjacency list. It's O of V square in an adjacency matrix. We already explained the reason why. In an edge list, it's going to be O of V times E. That will only make sense if you see the implementation, which we're not going. And space is O of V plus E here because they are stored a list of vertices. V square here because V by V matrix and no V because it's just. So for the fast class, adjacency list is better because you're not wasting a lot of space. The reason edges are much smaller than V square. They allow uh, BFS and DFS are faster. It's of V plus E rather than of V square. The matrix is useful for dense graphs. Constant time operations are uh, uh, manipulating having edges. Uh, they are expensive in BFS, DFS, and when you need to add it to
So the problem we are trying to solve here is search. So I'm only going to be doing this in terms of search time. We have seen ADTs and data structures. We split them into linear and non-linear ones. Linear ones I've taken this side. We are going to start here for list. I'm just taking average search time here. For all of these, it will take O of n to go to do linear search, right? So that is O of n for all these four implementations. Stack, Q, and DQ are efficient only at ends, and only at ends it will be O of 1. Otherwise, they are not concerned with searching for any particular element directly. Let's go ahead with trees. Binary tree, you do have to perform breadth first, BFS or DFS. One of that you're supposed to do, and it will take O of n time. Binary search tree, you know the root, so it will take O of h, where this is the height of the tree. AVL tree, we just made sure that the height remained to be log n base 2, so that you didn't have to deal with the worst case in the that we got in BST. B tree made this be optimized further by making it log n base m for n children, right? Then we went ahead with priority queue. We implemented that with min heap and max heap. This is only to find minimum or maximum element, right? Only for that it will take O of 1 time. If you want to find it again and again, it's going to take log n each time. But not for searching for a particular element, right? This is only when min-max is concerned. And then we have hash. We went to hash table. We found that it takes O of 1 time in most cases. So we are going to consider this O of 1. Graph for adjacency matrix, it's going to be O of B square. For adjacency list, it's O of B plus E. We just covered this. So yeah. And then final notes, if you just want to find a singular maximum or minimum element, go for linear search. If you want to find it repeatedly, go for heaps and keep popping off of that. And but for general search, we will be going ahead with this.